Hello, my name is Rob Reynolds. Welcome to Calculus section 2.7, where today we get the definition, a more accurate definition of a limit. And we're going to do proofs, which are not your T-chart geometry proofs, but there is a process that I'd like for you to follow when doing proofs. So the first thing I need for you to understand is the limit definition deals with delta and epsilon. They're called delta epsilon proofs. And here's the symbol for delta, and here's the symbol for epsilon. And so the actual definition says that there is some epsilon, and epsilon is nothing more than a very small y value. There's some epsilon that you can add that's very small, that's such that the function, the y value, is epsilon distance away from L. And that's how you read absolute values. And the same thing for x. There's some delta value that's very, very, very small as well, and x is delta away from A. So if this is A here, this little distance right in here is called delta, and this little distance here is called epsilon. Of course, we could add epsilon and subtract epsilon. So what you need to know is as delta gets really, really small and gets closer and closer to A, then that lowers these epsilon values and they get closer and closer and closer to the limit. And that's what's happening. You're letting delta be very small and epsilon even be smaller until you're very, very close. So for example, you want the y values to be some epsilon distance away from 5. And in example number 1, they say let epsilon be just 1. Well, 1 away from 5 is either 6 or 4. So there's one distance above and one distance below. And then so I'll try to name this point. It looks like this point might be 5 comma 6. And then this point is 1 comma 4. And the goal of this problem is to determine find some delta. And if delta, see, I need x to be some delta distance away from 3. So here's the 3, and then here comes my delta distance away. And I can see from 1 to 3, delta is 2 units. And I could have done it from this distance as well. In fact, you always just choose the smaller if they're not equivalent, which I'll show you an example of that. You always just choose the smaller. So here delta would be 2. In part B, we repeat the process. It looks like the epsilon is going to remain the same. So I still have the points 1, nothing's changing here. So I still have the points 1, 4, and 5, 6, but now they want me to have epsilon just to be a half. So it's a half a units away from, notice I'm changing this sign because x minus 3 equals 0 when x is 3. So it's a half a unit away from 3. So here and here. And as soon as I draw those lines, you can see the distance of delta is in this little space here, which is between 3 and a 4, 3.5. So delta is a half. And here's the book process of solving these. So again, the formal definition says epsilon is a very small number such that y is epsilon distance away from some limit y value, and x is some delta distance away from A. In this next example, we're actually going to pull out our graphing calculator, and they don't give you a graph, so we're going to see if we can just do this on our graphing calculator together. When we pull out our calculator, we'll type in this function x cubed minus 6x squared plus 12x minus 5. I'm going to zoom 6 it to see this, and notice that they want epsilon to be 1 in the first part A. So I need all the values of y that's 1 unit away from 3. And 1 unit away from 3 would be 4 and 2. So I'm going to look at y equals 4 and y equals 2. So let's pull back out our calculator and let's just graph y equals 4 and y equals 2. And I'm going to zoom in a little bit here so I can see a little bit better what's going on. Zoom to enter. And then the goal would be, let's go find those x values that correspond with those epsilons. So second, calculate the intersect, number 5. I'll guess the blue, I'll guess the red, and it says the intersect is 3, 4. And so my next goal, I'll just show you here. If I have one intersect at 3, 4, there's a little bit better graph of it. So here's the 3, 4, and now I'm interested in finding this x value, but I know that that is a 2 because I am one distance away from y equals 3. So this must be a 2. So I got to go find this x value. And again, you can do that pretty quickly on your calculator. Second, calculate the intersect, but this time choose the blue and then choose the black by hitting the down arrow and then press enter and then come over and tell me the intersect, which is a 1, 2. So x is 1. So trying to answer this question, I need all the values of x that are some delta distance away from 2. And so remember, this x value is a 1, this x value is a 3, and some distance away from 2. So here comes my delta, and obviously this distance here between 2 and 3 means delta equals 1. Repeating this process, all I have to do is keep the same function, but instead of 4 and 2, I'm going to only let delta be a half a unit, so I'm going to choose 3.5 and 2.5 for my graphs. Again, what I'm doing is I'm looking right here and knowing that it's a half a unit. I need the y values that are a half a unit away from 3. So y sub 2 would be 3.5, half a unit above, and a half a unit below 2.5. And then I'd use my calculator again and calculate, second, calculate the intersect. And it looks like 2.79. And second, calculate the intersect of the blue, down arrow, hit enter for black, and then find the intersect, and 1.2. So what did I say? X is 1.21, or X is 2.79, and I'm finding the distance away from 2. So I could do 2 minus the 1.21 to find the distance, or I could do a 2 minus the 2.79. Remember, distance is absolute value. So I'm looking for some delta, and that should be the same distance. If it's not, again, you choose the lesser. But I think this is symmetrical, so it's about 0.79 for the distance. Let's see if the author, yep, the author agrees. So something between 0 and 0.79 for delta. Example 3 is a great example. If you haven't downloaded the worksheets, I would download the worksheets, try to work it out. I think you'll be okay. I'm going to skip it for the sake of the length of this video because I need to get to the proofs, but I would highly recommend that you try to work this one out. It's pretty straightforward. And then, of course, I have solutions here, and you're welcome to work it out and see if you don't get delta to be equal to half of epsilon for that example. But let me get to the delta epsilon proofs for you. We're literally going to use these definitions that we've been doing, which you'll need to have memorized for your quizzes and tests. I will not give those to you. So you'll need to have these delta epsilon definitions memorized for your proofs. And so for your first look of this delta epsilon proof, we always start with the definition. It's a two-step process. So I like to start here, step 1 and step 2. Step 1, we'll start with the definition, which is the f of x minus the limit is less than epsilon. And we'll plug in the function, and in this case, the function is 4x minus 15. I'll literally subtract off the limit, L, and here it says the limit approaches 1. So I know that the limit is 1, and it's less than some epsilon, which we need to go find. And so let's go find it. So 4x minus 16 is less than some epsilon. I can actually factor out a 4. And maybe you don't know it, but the absolute value of 4 simply is 4. I don't know the absolute value of x minus 4, so I can't pop that out, but I can divide both sides by 4. So the absolute value of x minus 4, let's call this what it should have been, which is epsilon divided by 4. Now, a hint to this is um, this guy should match your step 2 definition, which always says 0 is less than some x minus a value, which is less than some delta. Well, look at this. This is x minus a, and lo and behold, a is what that's approaching. And so this number, this 4, better match this a value, which it does. So I'm very happy with this. So now I think I can just walk backwards. In fact, I'm just going to do a little let statement here. Let's let delta equal epsilon divided by 4, which I discovered here. And then to this is the actual proof over here. Over here, I was just finding some delta. After you find some delta, here comes the proof. We're going to let delta be epsilon divided by 4 and simply walk ourselves backwards. We're going to let a be 4 because that's what it tells me to be. And we're going to prove that this equals 1 for the limit. And we can do that by multiplying both sides by 4. Of course, that just stays 0 over here. So distributing. And then the tough part is maybe trying to figure out what to add or subtract to this because that's not quite the function. I need to get to a 15. So you can see 4x minus 15 minus some L has to be, well, what does the L have to be? Well, we decided the L has to be a 1, and sure enough, it is, because that gives me the 16. And to me, there's the function f at x minus the L, and if you take the absolute value of that, that is less than epsilon, and that's a good proof right there. The author kind of writes it out a little bit differently than I do. I like my method. You're welcome to use any method, but if you follow my method, it's easier for me to grade, and I think it's a little bit easier. So you can practice with all 3 of these. There's a little hint that I can give you about 21. When you're doing it, I think we want to simplify number 21 first by factoring it. So x plus 4, x minus 4 over x minus 4. And when you factor, the new problem just becomes, prove to me the limit of x minus 4 of x plus 4 really is 8. Well, of course it is, because if you do direct substitution, you get an 8, but that's not the proof. The proof is your delta epsilon proof, which you have 2 steps. So again, the first step is always to find delta. And to do so, we start with the formal definition. F of x minus L is less than epsilon. And in this case, the function is just x plus 4. And the limit is 8. And we want that to be less than epsilon. And hopefully when I get done, I'll find another 4, that blue 4, which is my a value. So let's see if I can't find that. Well, boom, I found it. This was an easy one. That's in the correct form already. So all I do is let delta equal epsilon. So now I'm ready for the step 2. And step 2 is the actual proof. So I start with 0 is less than the absolute value of x minus some a value, which they tell me is 4, which I'll fill in a moment, is less than some delta, and I'm going to let delta equal epsilon. Here it says that the a value really is 4. So x minus 4 is less than 0. This is a less than. And, well, I need to get it back into the form that I needed. So really, I'm just reading this backwards. You just rewrite it, everything backwards for the proof. So you really have the proof complete. You just need to write everything backwards from the process that you use to find delta. So I'll write this backwards, and sure enough, this becomes there it is. There's the function minus the limit is less than epsilon, and that's your proof. I hope you found this video helpful. If you have questions, shoot me an email.